Hello and welcome to my YouTube channel. We're talking about another kind of operational amplifier, which we refer to as an integrator or integrator operational amplifier. So when it comes to this type of operational amplifier, it's being designed as a result of modifying an inverting operational amplifier. But you can see here, if this were to be an inverting operational amplifier, we have here as RF, right? Being the feedback resistor. So what we do is that we take an inverting operational amplifier, then we replace RF with what CF, right? Meaning the feedback capacitor that we have here. And as a result of doing this, then we end up having or getting an integrator as a result of this process. So how do we get the equation, right? That is going to connect the output voltage and then the input voltage, known as here as Vin. So we go through the same process again. So we have V1 being grounded, that is the non-inverting input terminal is grounded. That is V1 here. As a result, V2 is also grounded as well because of virtual ground. Then you have node A, which is going to be the interconnection or the junction where two or more components are connected. And that node A is, you can see that it's also connected to the inverting inverting terminal here. And there we label that we have what V2 in there, and we know V2 is 0 because of what virtual ground, because V1 is grounded. Then as a result, VA also becomes 0, meaning the voltage at node A is also 0. Then we apply Kirchhoff current law at node A. Then we get the same equation as we did under both integrator and then inverting operation. But we get I equals to I plus IF, and I mean equals 0 because we are dealing with operational amplifier with an infinite gain, for example, infinite open loop voltage gain, which means in order to achieve that, that means the differential voltage equals 0. Then you have, that means you have a situation whereby the input resistance is what? Infinite. And as a result, you have less amount of current passing through the operator. So we have IN is 0 in that situation. So we have IN equals to IF. And again, we come here, we can now use our knowledge of potential difference to get the current IN and then IF. So when it comes to IN, it's just we take in where the current originates, that will be the high potential voltage, where the current is coming from the high potential, where the current arrives is a low potential. So we have here Vin is originating from V, IN is originating from Vin, so that makes Vin being the higher potential here. Alright, then the current arrives at node A, so voltage at node A becomes the low potential. We take that potential difference, Vin minus Va, all over the resistor, which is between the two voltages, and that is what Rn. That will now be equals to what? The feedback current, which is IF, and IF, yes, can see here again, we have a capacitor, and when it comes to a capacitor, the current passing through a capacitor will equal to the capacitance times the rate of what? Change of what? The voltage, that is the V over the T. Then we just replace that principle here. And when it comes to the voltage here, that will also be inside here the potential difference between the two voltages. So we can see that IF is originating from node A. So node A becomes the higher potential, then current arrives at VO. So the output voltage becomes the low potential. So we have VA minus VO. So you can see here we get minus. So you take the minus out, we end up getting this relation. And from there, again, we are interested in the output voltage. And that means we make output voltage the sum, that we get output voltage mean equals to integral of negative V in over I in times what? CF, which is the feedback capacitance, then the T here times the T. That means we are integrating with respect to time. You are giving an input voltage V in, so integrate it with respect to time, then you multiply it by what? R in, by negative of what? 1 over R in and CF. Those are constant values, and this is how you end up getting an integrator. See you in the next video. Bye-bye.